In this section, we're going to carry on working our way down the OSI reference model, and we've now reached layer 3, so you'll learn about the network layer. We are going to cover the format of the IP header and also the format of IP addresses. You'll learn about the different types of traffic we can have on our network. That's unicast, broadcast, and multicast. And you'll also learn about the subnet mask and about how it defines the boundary between our different subnets. In this lecture, we're going to cover layer 3 of the OSI model, which is the network layer. The network layer is responsible for routing packets to their destination on the network. So this is why routers operate at the network layer. And it's also responsible for quality of service as well. What quality of service is, you might have one particular type of traffic that requires a better level of service than another level of traffic. For example, if you're running voice or video over IP, it's sensitive to delay, so we're going to give it better quality service than something like email. IP, Internet Protocol, is the best known layer 3 protocol. IPv4 is the focus of this section. There's also IPv6 as well, which is the upgrade for IPv4. Later on throughout the course, we'll be talking about why we have IPv6 and also its actual usage today and how to configure it. IP is a connectionless protocol, so there's no acknowledgements at layer 3. You can still have reliable traffic by using TCP and its acknowledgements at layer 4, or by having it built into the upper layers. Other layer 3 protocols, apart from IP, include ICMP, which is the Internet Control Message Protocol, which is used for ping for troubleshooting, which we'll also be talking about later in the course, and also IPsec for secure encrypted communications. There are other protocols as well, but IP is the best known one, by far the most commonly used. That's what we're going to be talking about in this entire section. IP addressing is a logical addressing scheme which is implemented at layer 3. So the network designer uses IP addressing to partition the overall network into smaller subnetworks, or commonly called subnets. By having different subnets, it improves performance and security and makes troubleshooting easier. It improves performance because rather than having one big flat network, we divide it into smaller subnets and we can keep the traffic on the particular subnet that it needs to be on rather than going everywhere. So we get better performance that way. We also get better security by having this logical addressing as well. For example, let's say that we've got accounting servers. We can put them on one particular subnet, and that makes it really easy to control who's got access to those servers. Also, it makes troubleshooting easier as well, because by partitioning the network into smaller parts, if we have a problem, it's easy to see what part of the network the problem is on and concentrate there. So that's our layer 3 addressing, uses IP addresses. At layer 2, which we'll get to soon in the next section, we have MAC addresses if we're using Ethernet. IP addresses layer 3, MAC addresses layer 2. IP address is a logical addressing scheme. MAC addresses is just one big flat global addressing scheme. So you'll see this section is going to be a lot longer, more involved than when we get to MAC addresses, because there's a lot more work to do here. There's no logical separation at layer 2 of the OSI model. It's done here at layer 3 with our IP addressing. Okay, this is the first lecture in our layer 3 section. So as usual, we'll have a review of the OSI stack again. You're going to see this several times because it's important, and I really want to drill into you about how networking works based on the OSI model. So again, we've got the 7 layers. Layer 7 is the application layer. When a sender is going to send traffic, it composes the packet. It creates the layer 7 information first. That then gets encapsulated in the layer 6 presentation layer header, then encapsulated in the session layer header. Top 3 layers are our upper layers, mostly the concern of application developers. As networkers, we start getting really interested at layer 4. So the packet, we've got layer 765, it then gets encapsulated with the layer 4 header, and that will either be a TCP or a UDP header, and the port information will be on there. That then gets further encapsulated in the layer 3 header, which is the subject of this section. Main information in the layer 3 header is the IP address information, but you'll see coming up shortly the rest of the information that's also in the header. Our network infrastructure device that works at layer 3 is our routers. Then we carry on making the packet. We put on the layer 2 header, which is the data link header, on a local area network that will be using Ethernet, and will have the source and destination MAC address there. Our network devices that work at layer 2 are our switches. Finally, the packet will actually get put onto the physical wire. That's at the physical layer, and our hubs work at the physical layer. Not that we still have hubs. We'll talk about that a bit more later too. Okay, last slide in this lecture, we're going to take a look at the IP header. So the top row that you see there, first part is a 4-bit version. It's either going to be IP version 4 or IP version 6. That's referenced in that field. We then have the 4-bit header length, the length of the IP header. It can be a different length because the header options that you see further down can be variable length. We then have the type of service byte. This is used for quality of service information. So we can put a marking on the packet to specify what kind of traffic this is. And on our routers later, we can take an action based on that marking to give it better service if we need to. For example, for our voice over IP traffic. We then have the 16-bit total length of the packet. The next row underneath is used for fragment information. With our different media types, for example, Ethernet, there is a maximum transmission unit size, the maximum size of the packet. Maximum size by default in Ethernet is a 1500 byte MTU. If we try to put a packet onto the wire that is larger than that size, it has to get split up into smaller parts, which are called our fragments. The second row of information on the IP header is used to help keep track of those fragments. The next row down, we have an 8-bit time to live field. Every time a packet goes through a router, the router will decrement the TTL field by 1. If it gets down to 0, then that router will drop the packet. What this is for is to prevent routing loops. We might have an error in our network somewhere that is causing packets to endlessly loop around the network without ever getting to their destination. We don't want packets to loop around forever, so TTL will prevent that and drop them. Now, it doesn't fix the underlying problem. We still need to cure the loop so that traffic will actually get there, but it stops us from having a huge amount of traffic getting built up on our network, slowing it down, which is just looping. The next field, the 8-bit protocol, that will specify the layer 4 information type, typically TCP or UDP. We then have a checksum, which is used to check that the packet has not been corrupted in transit. Next, we have the source IP address, specifying where the packet came from, and then the destination IP address, specifying where the packet is going to. The next field is the header options, where we can put in additional information. It's not commonly used. And finally, we have the data, the rest of the packet. Okay, so that is the basics of layer 3 and the IP header, but I've got a lot more information to tell you here, so I'll see you in the next lecture. In this lecture, you're going to learn about the 3 main types of traffic that will send over an IP network, which are unicast, broadcast, and multicast. Unicast traffic goes to a single destination host. Broadcast traffic goes to all hosts on the subnet, and multicast traffic goes to multiple interested hosts. So let's have a look and see how this works. So the first example here is going to be unicast traffic. I've got the sender over on the left, and it sends some particular traffic to the PC up at the top of the picture there. And it also sends some other traffic to the PC up at the top right. So unicast traffic, it's coming from a sender and it's going to one particular host, so unicast. The next traffic type is broadcast traffic. So with broadcast traffic, the sender sends one copy of the traffic that will come into the switch, and then it gets flooded out to all other hosts on that particular part of the network. So you see here, it goes to all of the different PCs that are attached to the switch. There's only one copy of the traffic that gets sent everywhere. You'll see it also hits the router in the middle there, which has got an interface, which is on that network. What happens then is the router will drop the traffic. So routers do not forward broadcast traffic on. You see the other two interfaces on the router, we don't forward the broadcast traffic out the other side of the router. This is a good thing because if you think about it, like with the internet, imagine if you sent out broadcast traffic and it got sent to everybody on the internet. Well, there's a lot of broadcast traffic, and that would really badly affect performance, and also we could say there's security concerns there as well. So broadcast traffic, one copy gets flooded everywhere throughout that particular part of the network. The next traffic type we're going to cover is multicast, but I want to just mention about how unicast traffic works to multiple hosts first, because this is going to help you understand why we have multicast traffic. So let's say the sender over on the left, it's going to stream out some video traffic, and let's say the bandwidth of the video stream is 1 megabyte. So it sends it to the PC at the top. It also sends it to the PC up at the top right, and it's sending separate copies of the same traffic to each of those individual hosts. It also sends it to the PC over in the middle on the right as well. So we're sending a video stream, it's 1 megabytes in bandwidth, we're sending 3 separate copies of it, so that would take 3 megabytes worth of bandwidth from the host over on the left, also throughout that part of the network as well. With multicast, we send one copy that goes to multiple different destinations. So you'll see how this works. Now the sender sends one copy of that same video stream, and that one copy then gets sent out to all of the interested receivers. So now, rather than sending 3 separate copies, taking up 3 meg in our example, we send one copy. It only takes up 1 meg, so we've got good bandwidth savings there, but it goes to everybody that's interested. The difference between broadcast and multicast traffic is that broadcast traffic goes to everywhere on that particular part of the network, whether the receiver has requested it or not. Multicast goes to multiple receivers, but it's targeted. They have to request it before we're going to actually get it. And a good analogy for multicast traffic is you can think of it like tuning into a radio station. So all of the different receivers, they've tuned into that particular station, they're going to get that particular traffic. Okay, that's it. That's our unicast, our broadcast, and our multicast traffic. IP addresses are written down in a decimal format. But to understand how they control the logical separation between networks, it really helps if you think about them the same way that a computer does, and that is in binary. So in this lecture, I'm going to show you how to convert decimal numbers into binary, and that's going to help understand IP addressing as we work through the rest of this section. As humans, we're conditioned to count in decimal. It's how we're taught to do it from a really young age, and we do it now without thinking about it. When we write a number down, for each column in the number, we have got 10 possible choices from 0 through to 9. And every time we add a column to the left, the value is multiplied by 10. And we start with ones as the furthest right column. So let me show you what I mean. So when we write down a number, starting from the right-hand side of a number, we've got the ones there. The next column is the tens. Then we've got the hundreds, then the thousands, then the 10,000s, and so on. So you can see that it's being multiplied by 10 each time we add a column to the left. If we were going to write down the number 236, the way that we do that is starting from the left now. So starting with the 1000s column, how many 1000s can we fit into 236? Well, obviously that's going to be a 0 because 236 is a smaller number than 1000. So we can't fit any 1000s into 236. That leaves us still with 236 left over. Next up, how many 100s can we fit into 236? Well, we can fit two 100s into 236, and that leaves us with 36 left over. Next up, how many 10s can we fit into the 36 that was left over? We can fit three 10s into 36. That leaves us with 6 left over. And then how many 1s can we fit into 6? That's obviously 6. So that gives us the number of 236 is how we would write that down. Now, like I said at the start of this lecture, that's completely obvious and intuitive to you. So you're maybe wondering why I'm breaking it down like that. Well, it's because binary is not obvious and intuitive, but it works the same way. So seeing how it works with decimal is then going to help understand and see how it works with binary. So computers don't work in decimal, they work in binary. And electrical impulses are either off or on. So there's only two choices, a 0 or a 1, unlike the 10 choices that we have in decimal, which is 0 through to 9. And every time we write down a number in binary, for each column in the number, we've got two possible choices. That's a 0 or a 1, rather than the 0 through to 9 that we had in decimal. And every time we add a column to the left, the value is multiplied by 2, rather than multiplied by 10 as it is in decimal. So looking at the columns in binary now, again, we've got a 1 on the furthest right, the same as it was in decimal. Then we multiply that by 2, so the next is 2. Then we've got 4, then we've got 8. So we just keep multiplying by 2, just doubling it each time. Next would be 16, then 32, then 64, then 128, then 256, then 512, and so on. So you saw how to write down 236 in decimal before. Now let's see how to write 236 in binary. And you can see on the slide here that the number we're going to get in the end is 11101100. So really not intuitive like it is with decimal. But we do it the same way. So rather than seeing how many we can fit in, it's either going to be on or off, 1 or 0. So starting off with 256 here, does 256 fit into 236? Yes or no? Well, no, it doesn't. 236 is a smaller number than 256. So we can fit 0 256s into 236, and that leaves us with still 236 left over. Next up, can we fit 128 into 236 or not? And the answer is yes, so that gives us a 1, and we've got 108 left over, because 236 minus 128 is 108. So next up, does 64 fit into that 108 that was left over or not? Yes, it does, so we put down a 1, and we've got 44 left over, because 108 minus 64 is 44. Next up, does 32 fit into the 44 that was left over? Yes, it does, so we have a 1 again, and we've got 12 left over now. Next up, does 16 fit into 12 or not? No, it doesn't, so we put a 0 down, and we've still got 12 left over. Then, does 8 fit into 12 or not? Yes, it does, so that's a 1, and we've got 4 left over. Then, does 4 fit into 4? Yes, it does, so we put a 1 down, and that leaves us with 0 left over. So obviously the other two digits are going to be a 0 and a 0 because 2 and 1 do not fit into 0. So you can see there that when we've got it written out, that comes out to 111,011,00. That is 236 in binary. As a final check, you should always have 0 left over. So if you get down to the 1 column and you've still got digits left over there, that means that you've made a mistake, so you should go back and do it again. You can also do a final check of your answer as well, where you do add up all of the columns where you've got a 1, add them all together, and that should total up the number you were looking for. So in our example here, we've got a 1 in the 128, a 1 in the 64, a 1 in the 32, in the 8, and in the 4. So if we add up 128 and 64 and 32, add 8, add 4, that equals 236, which was the number that we were looking to calculate. Okay, next up, let's check that you understood that and you can do it. So what is 179 in binary? I'll pause the video here, write down what is 179 in binary, and I'll be back in a second to check that you got it right. Okay, so how did you get on? The easiest way to do it is to get a pen and piece of paper and write the columns down exactly like you see on the slide here, and then just go from left to right as you saw me doing it in the last example. So figuring out 179 in binary, does 256 fit into 179? Yes or no? No, it does not. So we put down a 0, and we've still got 179 left. Then does 128 fit into 179 or not? Yes, it does. So we put down a 1, and we've got 51 left. Then does 64 fit into 51? No, it does not. So we put down a 0, and we've still got 51 left over. Then does 32 fit into 51 or not? Yes, it does. And 51 minus 32 is 19. So we've got 19 left over. Then does 16 fit into 19 or not? Yes, it does. We put down the 1, and we've got 3 left over. Does 8 fit into 3? No, it doesn't. So we put down 0, and we've still got the 3 left over. Does 4 fit into 3? No, it doesn't. So again, we put down 0, and we've still got 3 left over. Then does 2 fit into 3? Yes, it does. So we put down a 1, and we've got 1 left over. And finally, 1 does go into 1, so we put a 1 there, and then we've got our 0 left over. So writing down 179 in binary is 10110011. Okay, so that's it. That's how you convert from decimal to binary, and that's going to help as we go through the rest of the section. See you in the next lecture. In this lecture, you'll learn about the format of an IPv4 address. And when we write out the IP address, we write it out as a set of 4 octets in a dotted decimal format. So you see an example of an IPv4 address here, 192.168.10.15. Each of those sets of numbers is an octet. So 192 is the first octet, 168 is the second, 10 is the third, and 15 is the fourth octet. Each octet is 8 bits long. 8 bits, that's why we call it the octet. And if you multiply 8 times 4, that gives you your 32 bits, which makes up the IPv4 address. Okay, first thing I want to do is show you where you can find out the IP address on your different hosts and devices. So let's look in Windows first. So I'll open up a command prompt here. So CMD to open the command prompt, and the Windows command to see your IP address is ipconfig. And I've got a load of output on here because I'm running VMware on my laptop too, so I've got a lot of virtual addresses on here. Let's scroll back a bit until I find my wireless network. This is the one I'm actually connected to my network on. And here, if I mark this, you can see that my IPv4 address is 192.168.1.9. My subnet mask that you'll learn about in the next lecture is 255.255.255.0, so that's also in dotted decimal format. And the default gateway, which is the router that my PC would use if it needs to get out to a different network, is at 192.168.1.1. Now, I'm going to tie this all together when we get to the section later, which is called the life of a packet. And in there, I'm going to detail how traffic gets from the source to the destination. For now, I just want you to know that if traffic is going to another host on the same subnet, then it can go there directly. If traffic is going to a host on a different subnet, it has to go there via a router. So you can see my IP address is 192.168.1.9. That's the IP address on my laptop here. The IP address on the router I would use to get out to other networks is at 192.168.1.1. The other information you can see here as well is my IPv6 address and also the IPv6 default gateway. We'll be talking about IPv6 in a later section. Okay, so in Windows, ipconfig to get that information. Let's have a look on Linux as well. So I'm going to open up an SSH session here to a Linux machine that I've got running. And I'll get the command prompt on Linux. I'm going to enter my username and my password. And then the command to see the IP information on Linux is ifconfig. So ipconfig on Windows, ifconfig for interface on Linux. And you can see here that the IP address on this Linux host is 172.23.4.2, and the subnet mask, the same as it was on Windows, 255.255.255.0. Now in Windows, ipconfig will show you the IP address, the subnet mask, and the default gateway, which is the local router. In Linux, it shows the IP address and the subnet mask. To get the default gateway, the command is iproute, and you can see here the default route for my default gateway is 172.23.4.254. Okay, so that's how you get the IP address in Windows and Linux. Finally, let's have a look and see how we get it in Cisco iOS. So I've already got an SSH session open here to a Cisco router. I'm going to enter the command enable to get to the enable prompt so I can see my show commands. And actually, I don't think I've configured an IP address on this router yet. Let's just check. The command for that is show IP interface brief. Oh, I have. Okay, so on interface fast Ethernet 0/0, you can see the IP address is 192.168.10.1. To get more information, because this is only giving me the IP address, I can't see the subnet mask here. So let's do a show interface. I could do a show interface or a show IP interface. And I can see for fast Ethernet 0/0, the internet address is 192.168.10.1, and the subnet mask is a /24. The subnet mask can either be written in slash notation or in dotted decimal, and you'll find out about that in the next lecture. With my router, I don't have a default gateway on here, because your router, it's the device that knows about all the different networks, so it doesn't just point at one other router, it's going to have lots of routes in here. You'll find out about routing on the router in other sections a bit further on in the course. Okay, so ipconfig on Windows, ifconfig on Linux, and show interface on our Cisco iOS. It's the same commands for both our routers and our switches. Okay, let's go back to the slides. Next thing to tell you about is static and automatic addressing. On our important devices, like our fixed devices, like our servers, network infrastructure devices like routers, switches, and firewalls. Also on our printers, usually we will manually assign the IP address on there. For our laptops and our desktop PCs, they'll normally be assigned an IP address automatically through the use of DHCP, which is the Dynamic Host Configuration Protocol. We're going to cover how to set that up later on. The reason that you want your PCs to get their IP address automatically, if you imagine we're in an office with 6,000 people for a large company, you're not going to want to have to go around 6,000 different PCs and configure the IP address manually on all of them. You can centralize that through the use of a DHCP server. It's much more convenient. But for your fixed devices where you want to make sure the IP address is what you think it is and it's never going to change, like on your servers and on your routers, you'll do it manually on them. You're going to have much less servers and routers, so it's not so much hassle to manually set it there. Okay, to understand how the logical separation between our different IP subnets works, you need to understand the IP address in binary. That's why we had that binary lesson in the last lecture. Each octet in the IP address has a value ranging from 0 to 255. Let's see how we get that. So it's an octet, there's 8 bits there. Let's count them out. So 1, 2, 3, 4, 5, 6, 7, 8 bits. And it's binary, so the rightmost digit or the rightmost bit is going to be a 1, either a 0 or a 1, and then we're going to double each time we add a bit to the left. So it goes 1, 2, 4, 8, 16, 32, 64, and 128. It's binary, so we multiply by 2, we double each time we go up. And the values are going to range from 0 to 255 for each octet in our IP address. If we put a 0 in on all of those bits, obviously all zeros adds up to 0. If we put a 1 in on each of the bits, if you add these up, 128 plus 64 equals 192, 192 plus 32 equals 224, 224 plus 16 equals 240, 240 plus 8 is 248, 248 plus 4 is 252, 252 plus 2 is 254, and 254 plus 1 is 255. Now, if you're wondering how I was able to add those up so quickly and it didn't even look like I was thinking about it, yeah, that's right. When you get more experienced with networking, this is going to be second nature to you. IP addressing is really core to everything that you're going to be doing. So you're going to know IP addressing and its format like the back of your hand, just like I just showed you there. Okay, so that's how we can get the value is from 0 to 255. On each of those octets, the bit pattern in here on each of those different bits can be any combination that you want of 1s and O's. It goes from 0 at the lowest value up to 255 at the highest value. The example IP address I gave you earlier was 192.168.10.15. That's in dotted decimal notation. Let's convert that to binary. So the way that you do this is get a piece of paper and a pencil and write out what you see here on the slide. So starting from right and go to left, write out 1, 2, 4, 8, 16, 32, 64, and 128. And then to figure out what your IP address is in binary, start off with the first octet is 192. So we'll do that. And the first thing to do is you start going from left to right. So when you write it out, it's easiest to write it from right to left. But when you're figuring things out, we go from left to right. So the first thing to ask is, can 128 go into 192? Or is 128 equal to or less than 192? And yes, it is. So if that's the case, we put a 1 under the 128. Then what we do is we see what we've got left. Well, 192 minus 128 is 64, so we've got 64 left. We then go to the next column and see, does 64 go into 64? Yes, it does, so we put another 1 in there. We then take the 64 away and we're left with 0. Then does 32 go into 0? Obviously not, so it doesn't go, so we put a 0 there, and it's pretty obvious we've got 0 left, so we're going to have 0 on all of the rest of the columns. So 192, if we were going to write that in binary, it is 11000000. And then to do a final check, to check that we got this right, add these digits together. So add 128 plus 64. When we add them together, it comes up to 192, which is the value we wanted, so we know that we got that right. When you're working this out, if you ever get anything that does not end with a 0 value, you know you've made a mistake, so go back and try it again. Okay, so that was our first octet. Let's do this same process again for the second octet of 168. So does 128 go into 168? Yes, it does. So we'll put a 1 in there. And then the difference between 168 and 128 is 40. We've got 40 left. Does 64 go into 40? No, it doesn't. So we put a 0 in that column. Then does 32 go into 40? Yes, it does. So we put a 1 in there. And then 40 minus 32 gives us 8 left. 16 does not go into 8, so we'll put a 0 in there. 8 does go into 8, so we put a 1 in, and 8 minus 8 gives us 0 left, so we know we can just fill in the rest of the columns with a 0. So 168 in binary is 101010000. And our final check, add the numbers together. 128 plus 32 plus 8 does equal 168. So we got that one right as well. So the first half of our IP address in dotted decimal is 192.168. In binary, it's 110000.101010000. So hopefully you followed along with that okay. What I want you to do now is to stop the video and work out the last 2 octets yourself. So convert 10.15 into binary. And when you've done this, I want you to give me the entire IP address in binary notation. So what your output will be is 11000000 dot 10101.000 dot, and then the next octet in binary, and then another dot, and then the final octet in binary. So go ahead, stop the video now, and we'll check your answer in a second. Okay, so hopefully this is the answer that you got. 192.168.10.15. So the first octet was 11000000. 128 plus 64 equals 192. The next octet of 168 was 10101.000. 128 plus 32 plus 8 equals 168. The next octet, you should have got 00001010. 8 plus 2 equals 10. And then the last octet of 15, you should have got 00001111. 8 plus 4 plus 2 plus 1 equals 15. And if you look at the top of the slide here, that should have been your final output. That is the complete IP address in binary. Hopefully you found that really simple. With just a tiny bit of practice, you'll be able to do this without hardly even really thinking about it. Okay, so that's how we figure out the IP address. To set the boundary between our logical networks, our subnets, the IP address is going to be combined with a subnet mask. And you'll learn about the subnet mask in the next lecture. In this lecture, you're going to learn about subnet masks. And you can see what I've done here is I've opened up a command prompt on my Windows laptop again, and I've entered ipconfig, and you can see where I've highlighted it that my IP address is 192.168.10.15. My subnet mask is 255.255.255.0, and the default gateway is 192.168.10.1. So every host in your network is going to know what its IP address, its subnet mask, and its default gateway is. Let's now see how it's going to use that information. So onto the slides now. A host can send traffic directly to another host on the same subnet via the switches that they're attached to. But for a host to send traffic to another host in a different subnet, it must be forwarded by a router. So our routers are our devices that link our different subnets together and route the traffic between them. The host, therefore, needs to understand if the destination is on the same or a different subnet in order to know how to send it. If the destination is on the same subnet, it will send it there directly. If it's on a different subnet, it knows that it has to send it to the local router, which is the default gateway. And the way that the host knows whether the destination is on the same subnet or a different subnet is by comparing the IP address of the destination to its own IP address and subnet mask. The subnet mask, just like the IP address, is also 32 bits long, and it can be written in dotted decimal notation, the same as our IP addresses, or it can be written in slash notation. You'll see how that works a bit later in this lecture. A host's IP address is divided into a network portion and a host portion. And it's the subnet mask that defines where the boundary is between the network part and the host part of the address. And the easiest way to explain how this works is by giving you an example. So let's say the host's IP address is 192.168.10.15 and the subnet mask is 255.255.255.0. That's the IP address and subnet mask that's actually on my laptop. To figure this out, we write the IP address out in binary notation, like you learned in the last lecture, and then the subnet mask also in binary notation underneath. So our example was 192.168.10.15, subnet mask 255.255.255.0. So you see the top part here, I've written 192.168.10.15 out in binary, and then underneath 255.255.255.0 out in binary as well. The IP address is compared or masked with the subnet mask. A 1 in the subnet mask indicates that bit in the IP address is part of the network address, and a 0 indicates that the bit is part of the host address. So very quickly you can see here all the 1s on the subnet mask go up to here. Everything in the IP address above that is part of the network portion of the address. The 0s above that in the IP address, those are part of the host portion of the address. Let's make this a little bit clearer. So subnet mask 255.255.255.0. With the subnet mask, it's always going to have contiguous 1s, and you see the 1s come up to this part here. So I put a line in. That line is the border between the network portion and the host portion of the address. So in the example, the network address portion is 192.168.10, because on the IP address, from here on the left all the way up to the line, that is 192.168.10 part of the IP address. Whatever is after the line is the host portion of the address. So in our example, it is the .15 is the host portion of the address. And I've highlighted it there. There is the network portion. If the host wants to communicate with another host with an IP address, which also begins with 192.168.10 in our example, so say for example that this host wants to send traffic to a destination address of 192.168.10.20, it knows it's on the same subnet and it can send the traffic directly because the destination also begins with 192.168.10. If this host wants to communicate with another host on any other network, anything that does not begin with 192.168.10, then it knows it has to send the traffic via a router. So if it was sending traffic to destination 192.168.11.20, for example, it doesn't begin with 192.168.10, it's a different subnet, sends it via the router. For a destination address to be on the same subnet, the network portion has to be exactly 192.168.10. Anything else means it's a different subnet, we have to go via a router. The subnet mask always begins with a contiguous block of ones. This is different than the IP address. You see our example IP address here, it's 11000000100101. So with the IP address, the ones and the zeros can be mixed about in pretty much any order. The subnet mask is a block of ones and then a block of zeros, always. We never mix the ones and the zeros up with each other in the subnet mask. So 111111.1111.0000.000, etc. is a legal subnet mask. 111.011.0.1, mixing up the ones and zeros, we can't do that. That is not a valid subnet mask. The host portion of the address is available to be allocated to the different hosts on that particular subnet. For example, your PCs, servers, printers, router interfaces, switch management addresses, etc. With two exceptions that you'll see coming up after the next slide. So there's the host portion of the address for our example highlighted. The host portion of the address specifies the individual host and must be unique on that subnet. Your hosts do not need to be numbered sequentially. For example, we could have a subnet with two hosts on it. One could have address 10.10.10.10, the other could have address 10.10.10.20. We don't need to number them .1 and .2. You can't have two different hosts both with the same IP address. For example, we couldn't have two hosts both with address 10.10.10.10. That would be a duplicate address. And whenever any traffic was sent to 10.10.10.10, your network devices wouldn't know which host to send it to. So that's illegal. You can't have duplicate IP addresses. You could have host 10.10.10.10 on one subnet and host 10.10.20.10 on a different subnet. They're different subnets, so it's not a duplicate address. That's just fine. All zeros in the host portion designates the network address and is not allowed to be allocated to a host. Remember, we just said a minute ago that there's two particular addresses that cannot be assigned to a host. The first one of those is all zeros in the host portion. That designates the network address or the network ID. In our example, the network address would be 192.168.10.0. So we fill in the bit pattern in the network portion. So that was 192.168.10. And then in the host portion, we put all zeros in there. So all zeros, you can't assign it to a host. It signifies the network address, which is the bottom address in that particular subnet. And there's it highlighted there. You can see we've used all zeros. The other address which cannot be assigned to a host is all ones in the host portion of the address. So all zeros signifies the network address, which is the bottom address in the range. All ones, which is the top address in the range, that is the directed broadcast. Whenever you send traffic to the directed broadcast address, it goes to all hosts in that subnet, not to an individual host. So we can't assign that address to an individual host. And there it is highlighted, the host portion, I've put all ones in there. So that leaves 192.168.10.1 to 192.168.10.254 in our example available to be allocated to our different hosts. So all the different PCs, other kinds of hosts, maybe we've got some Windows PCs, some Linux PCs in that subnet, I can number them from 192.168.10.1 all the way up to 192.168.10.254. They're all in the same subnet. Whenever they send traffic to each other, they can do that directly without going via their default gateway router. Okay, we can also write the subnet mask in slash notation. 255.255.255.0 is writing it in decimal notation. So the example here, 255.255.255.0, we can write that out, the subnet mask, and you see there is the line between the network portion and the host portion. And as we covered earlier, it's always contiguous ones and then followed by a block of contiguous zeros. Because it's contiguous, we can count how many ones that we have in a row. So the example here, we have got 24 ones in a row. I know that each of these blocks is an octet, they each equal 8. So that's 8, 16, 24. So 255.255.255.0, we can write it like that in dotted decimal notation. Another way we can write it is slash 24. Those two things both mean exactly the same thing. If we had 255.255.0.0 as a subnet mask, we could write that as slash 16 and so on. And whenever you configure a Cisco router or switch on iOS, when you configure the IP address in the subnet mask, you have to write the subnet mask out in the full dotted decimal notation. But whenever we're having a conversation with somebody, or if we're creating a network diagram, more commonly we will use slash notation, because it's not much fun to be saying 255.255.255.0 all the time. It's much easier to say slash 24. Also, slash 24 takes up much less space on your network diagrams, so you can have your diagrams looking a lot neater and tidier. Okay, there was the network portion for a slash 24 highlighted. Let's look at another example coming up. Again, we're looking at the slash 24 there. So the other example is for IP address 10.10.10.15 slash 255.0.0.0. And hopefully you can just, by looking at this, you're going to see that that's going to be a slash 8. The more you get used to working with IP addresses and subnets, you'll very quickly be able to see where the lines are by just looking at the actual address and mask. So the example there, the IP address can be written as 10.10.10.15 space 255.0.0.0 or 10.10.10.15 slash 8 when we're writing it out in full with the subnet mask. In the example here, the network address is 10.0.0.0 slash 8. I've put this in bold to highlight it because the network address is not 10.10.10.0 slash 8. When we write this out, it's just the network portion of the address that we specify. So it's a slash 8, so it's only the first octet, which is the network portion, so that is the 10. All the rest of the address, the last 3 octets, is the host portion. So when we write this address, it would be 10.0.0.0 slash 8. And the available addresses would be 10.0.0.1 for our first host. The last host would be 10.255.255.254. We can't use 10.255.255.255 because that would be the broadcast address, and 10.0.0.0 is the network address. Okay, that was everything I needed to tell you about the subnet mask for now, but we'll be covering it in more and more detail as we go through the rest of this section.